All right. Good morning. Thank you very much for having me here. I'll talk about AI in a post-war era. So I understand this is a broad AI community, and I'm glad to be here. Thank you for an invitation. I'm going to talk a little bit about the foundations of AI, mostly from the electrical engineering perspective. So, what are the things that make AI work, like when you do your computation as if you do computation on pretty much for any other type of workload. Let me see if this works. I'm going to use my hands here. Okay, so for those of you who have been around for a couple of decades, the beginning of last decade, we had an era called the big data era. Big data was a huge revolution in computing, because we realized that we have a lot more data that we can really compute with. So we have to think about what to do with all this data. It turns out that a lot of good things were coming out of it. So first of all, big data meant that data is growing in volume. Big data meant that data has a fast growth rate. So the volume was also growing. Big data meant that we want to somehow turn that data into value. At the end of the day, it's all about economy, making money. That data also was already showing an impact on GDP. And we're seeing now AI in the past 6 to 8 years, which is the sort of the next wave of big data. There are, by some estimates, now we're going to be running out of data because we're building large language models that have pretty much used all of the public data that's available. And we might eventually mature with our AI technology to move on to dealing with data again. So data is basically served to us by data centers. So data centers, what are data centers? Data centers are basically 500,000 computers connected to each other. And these computers are primarily connected to each other as an investment to be able to create a service where we host the data and serve data, and we make money out of this. So today, in 2024, the investment in the data center space worldwide is about $300 billion. Now, the revenue from the cloud is $700 billion. So somewhere between $700 billion and $300 billion, there is a little bit of a profit. Again, that's what this thing is about. It's about centralization of data so you can exploit economies of scale, make a lot of money. This is a satellite image of a Microsoft data center. This image has not changed in the past 10 years. It's on Google Maps for security reasons, I think, but mostly it's a big data center. You could tell the dimensions is 200 meters by 2 kilometers. If you populate this with what we use as data center technology today, you have roughly around 300 megawatts of electricity in this data center, okay? That is the electricity consumption of the city of Zurich, all right? And so what is interesting about a data center is that it's, first of all, it's a massive computer. The actual insides of the computer is not that interesting because the goal is to make a lot of money, so we don't really make it technologically that advanced. We actually use simple technologies. But the connectivity is quite special because you can go from one end of this to the other end of it on wire in a few microseconds, which is interesting because every server by itself has at least tens of microseconds of access time to its own flash. So you can go from one server to another server faster over the network if you build proper connectivity, but on the wire, it's only a few microseconds, okay? You typically find electricity, internet connection, and cooling to build one of these things. Yeah, so that's what a data center is. And there are different types of data centers. They come in various sizes, various granularities. They also have various data protection and privacy frameworks. So the public clouds, you give all your data away, and you have global connectivity. Edge clouds, you're within a data protection or privacy framework, closer to the user, closer to the source of data. Now, what made this technology possible? It's what's called Moore's Law. And Moore was, rest in peace, a co-founder of Intel, passed away this past year. And he explained what this phenomenon is. It's an exponential improvement in density and also together with that in efficiency of silicon. So that means that every 2 years we get double the density. We can compute twice as much or we can store twice as much. And here is the first microprocessor from Intel, 92,000 operations per second, 1 watt. About several decades later, several orders of magnitude more operations per second, and only a couple of orders of magnitude increase in power consumption. So in 50 years, we have 13 million times faster processors and 48,000 times more efficient computing. Okay, so this is good. All exponentials slowly come to an end. Okay, so we're now witnessing the end of Moore's Law. That means that there is nothing exponential anymore. Why is this happening? Because we've reached the limits of physics in how dense we can make silicon-based chips. Now, let's look at AI. Okay, so this is a graph that plots the size of a large language model and how quickly it grows. It actually grows several orders of magnitude per year in the number of parameters. That's roughly the size of the model. That's roughly the amount of computation you need. Also, roughly how much you need to store it, and eventually how much bandwidth you need to move it. Okay, so these are various examples up to GPT-4, which is an estimate. Jensen Huang's chips are also growing in efficiency, and they can compute more, but they're not going as fast, right? So we see improvements between H100, H200, B200 that's announced. You get double the number of, eventually, I think a total of 8x from V100 to B200 in terms of number of petaops per kilowatt. Kilowatt hour is a unit of energy. So here's the difference between these two. Is on the one hand, the LLM is growing from 2019 to 2025 by 1,200x. On the other hand, the NVIDIA chips can compute about 8x since 2017. Okay, so there is growth in the chip, but the chips are orders of magnitude behind in trying to catch up with the LLM. If we look at the total energy consumption in data centers, and some of that is now going to be related to AI, total energy consumption in data centers has been pretty flat for about 10, 15 years because data centers continue getting consolidated, and there's a lot of improvements, one-shot improvements in energy, and energy efficiency was improving over a couple of decades until around 2019. And you see around 2019, we're now seeing a rough increase of 15% per year in energy consumption. Okay, so that's at 2019, we're about 200 terawatt hour per year. In 2023, 4 years later, we're about 400 terawatt hour per year, shooting up to 1,000 terawatt hour per year by 2030. That is the energy consumption of Japan. Okay? And part of that is due to AI, but not all of it is AI, and the AI part is also growing. Okay, so this is important to keep in mind. We also care about emissions, so it's important to know where emissions are from. In servers, data centers, emissions are mostly from operational use of electricity. and a little bit also because of embodied carbon. And embodied carbon is the energy we use to make the equipment inside the data center, right? So it's important to keep also in mind that anything we do in this conference and beyond to reduce the operational energy of AI and data centers is good. So what can we do? Well, we can think about what are ways in which we can improve our efficiencies, and there are really three ways in which we could do this. And this is what I call integration, specialization, approximation. Most of what we do is storing data, communicating data, serving data. Most of the cloud is about services that are directly delivered to the user, right? If you're a TikTok user or an Instagram user, most of that cloud revenue is centered around that. So most of the data is basically directly communicated to the user, and that user, there's an economic model associated with that data. Some of the data is also communicated to AI internally. So the data center is a data platform, delivers mostly data to the consumers, and it also delivers data to AI internally to improve those services. This data movement is a source of bottleneck. We spend a lot of electricity moving data, and so we need to find ways in which we reduce the data movement. We need to specialize our entire stack, software, algorithm, all the way to hardware infrastructure, so that we cut resources that have to do with processing data. And we also need to find ways in which we can approximate, which is we don't need to do everything perfectly in 32-bit precision, right? A lot of data is instrument data, is simulation data. A lot of it is analog in nature, statistical in nature. A lot of output is also statistical in nature, analog in nature. The output of AI is a statistical outcome, right? But we map everything to a digital representation. We compute digitally because it's been efficient, thanks to Moore's law. And then we map it back to analog, right? We don't have to use full precision everywhere. And eventually, we can also perhaps bring some analog computing to this pipeline. We don't have to convert all the time to digital. So we need to basically traverse the stack from algorithm infrastructure and implement these pillars. And we've had a center at EPFL called EcoCloud since 2011. We're looking at post-Moore data center design. In recent years, there's also a new mission of looking at not just sustainable computing, but also computing for sustainability and best practices, metrics, and methodologies. We'll talk a little bit about that. And we've had impact. We've had the first server-grade CPU using ARM cores coming out of the center. We've had cloud-native network and database stacks that optimize the efficiency of the service for a particular use case. And we've had liquid cooling from chip to rack. So we have two-phase liquid cooling in collaboration with our partners, IBM, coming out of the center. Okay, so let me tell you a little bit about post-Moore computing. By the way, this is a cartoon of a personal computer I had when I was a first-year master's student, early 90s, right? This personal computer had a CPU, had memory. The CPU was running at megahertz. The memory was 250 nanoseconds, roughly speaking. And then everything was on the OS side together with, every once in a while I had to go to the disk if something didn't fit. And when I was sending email, I would send out network packets over this legacy interface. By the way, this Linux was already there. These are earlier releases of Linux with Red Hat, with Debian. They're all coming out at that time, and they're running on these beautiful desktop PCs. If you look at today's server, it's basically a desktop PC. And Google wrote a paper about this. They said, look, we want to build a massive computer with desktop PCs, because these desktop PCs are super cheap, and we can build a massive computer just using software and connect them all together. And instead of one CPU, we have two CPUs. The CPUs are gigahertz. They used to be megahertz. The DRAM is only 5 times faster, but it's a lot bigger. And we have the same exact OS. It's the same, basically the same versions of Linux, same structure, same standards called POSIX. And now we have all these other equipment that we've put on that OS side because we don't have access to the memory where data is sitting, and we don't have access to the CPU. The CPU is basically holding the memory hostage. And Google wrote about this. The problem with this server is that this is a complete mismatch with what the data center wants to do. And we never fixed this problem because it's super cheap, so we're using it. We can fix it with technology. It will be expensive, okay? And we haven't fixed it for 2-3 decades now. The CPU and memory are running in nanosecond. Anything on the OS side is running in milliseconds. And most of the time, we want to go from the network or from one of these accelerators to the data, come back. We do a lot of copying, so everybody has their own memory now on the OS side, right? So we have this disparity in time scales by 3 orders of magnitude, 6 orders of magnitude. And we have these OS legacy interfaces and abstractions. The legacy interface is the PCIe, and the abstraction is POSIX. And you could see a lot of silicon is fragmented. Now, there are a lot of efficiency problems here to solve. There are a lot of really interesting problems, especially now that we're in the post-Moore era, where there's no easy way of building these fast computers anymore. You're not going to get much out of it. We need to think about how do we solve some of these problems in post-Moore era while keeping the cost low. So we still need to worry about the cost because the cloud is basically an economic model. It's not a technological advancement in computing. There is a hardware workload mismatch. We've written about it. Facebook also wrote papers about it. Google wrote papers about it, right? This was 10, 15 years ago, showing that the CPU we're using is a CPU that's designed for your laptop. That CPU was never designed to run the workloads that we run in the data center. Google also wrote about the data center tax, which is, okay, this is not a great hardware we run our software on, but to make the most out of it, we need to pack as many processes and services into a single CPU as possible. And they've claimed that they basically pack 20,000 threads per socket, okay? And when you pack 20,000 threads per socket, at some point you end up switching a lot. And that switching takes up 10% of your CPU cycles. And there are other sort of sources of overhead, virtualization, containerization. That adds another level of indirection that slows you down. RPC is the basic communication paradigm we use for software to talk to each other inside the data center. That RPC stack is pretty big. If you look at networks, they improve in bandwidth 20% per year. Look at projections from Mellanox from 10 years ago. They just keep growing. When your Moore's law slows down, your silicon doesn't get denser, software for communication becomes a bottleneck. You can no longer keep up with that network bandwidth. So you need to start looking at how do I harden the network stack. Microsoft has been announcing that memory is completely wasted in data centers, right? So memory is 50% of the cost of the server. 50% of the cost of the server is memory. Memory is wasted. If they look at the containers they sell in Azure or Amazon Web Services, Google, half of that memory is not used. When they rent containers in a CPU, they rent all of those cores that are inside the CPU. 20% of memory is left stranded. That's memory they don't rent, right? So a lot of waste of memory. GPU utilization for deep learning has about 50% utilization right now. There's a paper that just came out of Microsoft. It's a paper at ICSI this year that shows that There are 700 reasons why they found use cases of why GPUs are not properly used, not utilized. We'll talk a little bit about that. So what can we do for those of us who are young researchers? Well, there's plenty of opportunity to do server-centric CPU design, right? Nobody has looked at properly design a CPU for a server, right? This is just happening now. And a lot of interesting stuff is now all of a sudden coming out of Intel, AMD, and NVIDIA. And there are other CPU vendors as well. There are ARM vendors out there. There's also HiSilicon. You have massive request-level parallelism coming to the same exact services inside the CPU, right? You have billions of social media users are using the same service. These requests are all coming. They're basically running the same service. They're not in sync. The requests are asynchronous. They have nothing to do with each other, but they're basically running the same exact code over and over and over again. And I'm pretty sure for some of you who are interested in computer architecture, microarchitecture, you can think of ways in which we can build a proper CPU that deals with this parallelism. This is an unusual type of parallelism. It's not the typical parallelism we look at when we do CPU design. We can maximize the efficiency of our CPUs using proper metrics, throughput per watt, throughput per area, which we don't really look at when we do CPU designs. We need to bring the CPU, memory, GPU, and the network together, and that's what NVIDIA is doing finally. That's the one way you can deal with this integration problem is like bringing all these together. Once you bring them together, you get rid of a lot of copying, you get rid of a lot of overhead. You don't need to make transitions through the OS for them to talk to each other. You can just get them, keep them with close connectivity. And there are emerging chip-to-chip standards, UCIe, there's high bandwidth memory for AI. High bandwidth memory for the first time this year is making a lot of money. SK Hynix was in the news for several weeks. HBM is selling. Why is it selling? It's because of AI. AI has so much investment behind it that this expensive memory all of a sudden is making a lot of money. We're going to have rack level fabric. So NVIDIA is also integrating at the rack level. They're selling these things called superpods, right? We can look at the next level of integration, which is the rack, because right now we have these racks in the data center. They date back to the telegraph machines. These rack dimensions are from the beginning of last century. Okay, the maximum density of the rack is about 90 kilowatts. That's it. Not going to get more than 90 kilowatts. So to move forward, we need to think about how do we properly integrate the servers in the rack. Today, the racks are 42 units. Every server has exactly the same hardware in it. Why not disaggregate the hardware so that we can properly virtualize and share all of the hardware that's available to rack, make it available to everybody inside the rack so we can properly share that hardware. Rack level fabrics are emerging. So NVIDIA has their own, Intel is basically announced CXL, HiSilicon has their own, everybody has their own. These are rack level fabrics that allow you, give you connectivity. And eventually liquid cooling. So the biggest problem we have with chip design is that we've been power density bound for several decades now. And the reason why we're power density bound is, well, obviously Moore's law is slowing down, then our scaling died. We pack our silicon with a lot of SRAM. This SRAM is completely useless, and it's only there because we use air cooling. If we go to liquid cooling, we can dramatically increase the amount of logic we have compared to SRAM. We can improve the number of cores we have per silicon area by 1 order of magnitude. Okay, so and liquid cooling is coming. Why? Because of AI. So what NVIDIA is doing is basically bringing their CPUs and putting them next to the GPUs. Once you have liquid cooling, which is expensive for your GPUs, you can also use it for your CPUs and dramatically improve the power density for your CPUs. You could completely redesign your CPU that way. So that's something to keep in mind. We did this work about 14 years ago. This is the first server-grade ARM CPU that came out of my lab. If you look at today's server CPUs, basically they're desktop cores, and they're designed for single core performance. And nobody cares about single core performance in the data center space. Everybody talks about single core performance. They all report single core performance. Nobody cares about single performance. You only care about throughput with a given end-to-end latency. It's called SLO, okay? So if you look at these, this is Zen 3. You could see half of the chiplet is basically SRAM. Why? Because we're air cooling it. You have one half is memory, the other one half is these huge cores. They run at high frequency. Power is super linear at high frequency. You can run your transistors at lower frequencies with high threshold voltages. Power becomes linear with frequency in those regions, and those regions are the most efficient regions to use your electricity. If you now replace that with this ARM Neoverse V1 core, which is at 0.7 watts at 2 gigahertz, you get much better core complexity, efficiency from the core itself. With area density, you get much better energy efficiency from that core. You get much better throughput per watt. And you can also recover a lot of your power because you use these more efficient cores. You're running them in higher efficiency frequency regions with high threshold voltage devices. You can have a lot more cores. You don't need all this memory. And you get 1 order of magnitude improvement in overall throughput. AI has 2 workloads. Inference is online. It has tight latency constraints and doesn't really care about precision as much. Training is offline, and it's throughput optimized mostly and needs higher precision for arithmetic. The good news is that inference is variable in load at night, in the middle of the night, except for people like me who have jet lag. Nobody's using TikTok. During the day, you use TikTok, right? So can we take advantage of this load? Yes, if we build separate platforms for our inference and for training, then of course the load is also problematic. So we can build universal accelerators that do inference and training together. So this is the Coltrane project at EPFL. There are scaled numerical formats. These scaled numerical formats are good both for inference and for training. For training, they allow you to improve your arithmetic density because you're using block floating point or you use one scaling factor for the tensor. Most of your arithmetic dot products are in fixed arithmetic. And you could build accelerators with high density. For inference, you could deal with outliers in large language models. Large language models have outliers. If you go to quantized formats, you have large numbers that you cannot represent. You could do that with block floating point. And it works well with sparsification. We have a paper on that. You can read about it. It works well. You could do 4-bit training. We have a collaboration with Yunho Oh here at Korea University. We're doing 4-bit training with block floating point. And you could build prioritized accelerators where you do inference and you could do training or fine-tuning jobs in the background. And AI runtime has huge opportunities. For those of you who are interested in distributed systems, you're interested in software, this paper from ICSI, this year is from Microsoft, they show that there are 700 specific cases of bottleneck in GPU utilization. There is lack of proper batching, lots of CPU-centric tasks in the middle, high data transfer, latencies between CPU and GPU that are exposed, problems with communication, right? We need elasticity. Today's GPU clouds are containerized, and they rent the containers for a month. You rent a container, it's a static assignment of resources. You're not going to use it properly, right? If we could build distributed systems that are elastic and grow with the demand, both the GPU, the memory, and the network. We need metrics and methodologies. We don't have proper metrics and methodologies for efficiency. How efficiently are we computing for a given output, right? How efficiently are we loading our hardware? We gave examples in the previous slide. And then for those who are designing, what are proper design metrics for efficiency? We don't really have proper design metrics, and this is all new and is needed now. This is a initiative from Hugging Face. They call it AI Energy Star. They want to come up with a classification of models and use cases and how much electricity they use. And this is super interesting because it tells the customer, the user, if this is your application, you use this particular model, and that is the amount of energy you need for that model, as opposed to use the same model for everything, okay? So this is a good starting point. If you're interested, please go to the Hugging Face AI Energy Star. We have a platform also. I have this nonprofit organization called the Data Center Efficiency Association. We have 3 calculators for data centers. They do include AI, they do include GPUs. We have a calculator for DC efficiency, how efficient are energy flows inside the data center. Do we do heat recycling? Do we have on-premise renewables? We have a calculator for IT. So when we deliver 10 kilowatts to our rack, we have a calculator that tells the customer, here's how efficiently you're using those 10 kilowatts to compute. And we have a calculator for emissions, for the sources of electricity coming in. That's it. So AI's energy requirements grow exponentially. Moore's law of silicon is dead. We need post-more technologies and metrics and best practices, and integration, specialization, approximation are ways we can improve technology. And thank you very much.
Thank you so much for a great talk. I'm a computer vision guy, but I keep encouraging my students to work on systems. but anyway, so I guess my question is, you're talking about the post-Moore architecture, but another side is, but does that assume that you're still maintaining this von Neumann structure that we've been using for the last 100 years, maybe? Because people are thinking or talking about OS completely being replaced by AI itself. So now, in a way, AI itself is just an application. It's on the application level. But when AI actually comes below that level, and now is an OS itself, and you could probably call AI equals computer itself. So if that comes to reality, does the computer architecture that we know of exist? Or can you think about just a totally new architecture?
It's a very good question. So first of all, AI or no AI, silicon-based technologies will be here for another several decades, just because of pure investment. I mean, there is this thing called the Gartner curve, which means that any new technology coming will take a few decades before it breaks even economically. So silicon-based technology will be there. Now, what is von Neumann computing? Von Neumann computing is that you have your program and your data in memory, and you perform operations by fetching the operation, and then fetching the operands, and then writing back. GPUs address the von Neumann bottleneck by getting rid of the fetching of the operation, because they only fetch it once every 10,000 times. So that's good. And then they apply the same thing on the operands. Systolic arrays get rid of the second bottleneck, which is fetching operands from memory and writing back, by passing the operands directly from one compute element to the next compute element over wire. That's the end of basically von Neumann once you have systolic arrays. After that, there's nothing else. So you have to completely change your computational paradigms. AI taking over the system is a good thing. I don't think it's a bad thing, but I don't think that that fundamentally changes these 3 basic architectures we have. Right? Those are the 3, and we have to live with those for the next several decades. Definitely well below my retirement, so I'm not too worried about that.
I have a question. Thanks for your talk. Mm-hmm. First of all, it seems like designing the CPU become a lot more important than past right now. So it seems like the NVIDIAs and the Amazons are trying to making their CPU for the AI centers. So it seems like the NVIDIAs are trying to put the CPU right there for their products. So do you think that it's in future there's going to be more like diverse design of the CPU rather than just what we are living right now? And the other question is that it seems like you are trying to think about the environment based on how much they use in the energy in the AI centers. What kind of like do you in Europe's countries are they trying to like reducing the like what's the effort they are doing to reduce the energy cost it required to running
Okay.
the AI applications?
Okay, so those are two very good questions. Let me see if I can answer them one at a time. So first one is, why are you bringing, what is there to do with the CPU? Just, even if you don't change the CPU, but can you bring back my slide, please? Don't know if we can show. Yeah. So, yeah, I lost my slide. Thank you. So, if you remove this OS from here and connect your accelerators and memory and NIC directly together, right? So everything becomes red in that world, right? It's a fully integrated, it becomes a fully integrated substrate, right? You're already improving orders of magnitude in efficiency here because you're not even doing the OS crossing. You're getting rid of all the copying of data where most of the efficiency problems. So without even changing the microarchitecture, if you just create better connectivity, you're already ahead. And we've done about 10 years of research on this, so there's plenty of things you could do, and NVIDIA is doing it now for the first time. Besides that, the CPU microarchitecture itself, most of the CPU microarchitecture is low-hanging fruits right now. Nobody has looked at CPU microarchitecture for servers ever, right? We're basically taking these cores we're designing for the laptop, for the phone, and we're bringing those into the server. So there's a lot of opportunity there to look at how do you properly design CPU microarchitecture for servers. Now, going back to the question about energy efficiency in Europe, so if you look at the data center basically has this infrastructure to house your computers. That infrastructure has a metric, it's called PUE, power usage effectiveness. And power usage effectiveness means how much of your electricity is going into cooling, it's going into your UPS system, anything that's housing the servers, how much extra electricity you're putting in there. And there are companies in Europe that build data centers where the PUEs are already below 1.2. So we've certified some of these data centers in Switzerland, right? So that means that less than 20% of your electricity is going into the campus itself, and about 85% of the electricity is going into the servers, right? Nobody knows where that electricity is going, whether it's Europe or whether it's Korea or whether it's anywhere else in the world. The only people who know where that electricity is going are hyperscalers. That's Google, Amazon, Microsoft, because the cost of electricity is factored into their economic model, right? Anybody else who's running a data center, whether it's a private data center or whether it's a co-locator data center, they have no idea where that electricity is going. That's where we're coming in with our calculator. We're trying to help them figure that out. Any other questions?
Yeah, I think that's the end of this session. Thank you very much
Thank
for
you.
Professor Babak for your talk.